the introduction to how gases behave. You should already be somewhat familiar with some of the properties of gases. For example, if you just think about the air about you, there's really not much there. So one of the things about gas is that they're mostly empty space. And so in this empty space are a few little particles, we call them atoms, or molecules if it's more than one atom hooked together. And so they're a small part of the gas. Most of it's empty space. So the volume of gas is basically whatever size container it is, because gases like to expand forever. And the reason they expand is because the gas molecules are moving. They're not just sitting there not doing anything. So gas molecules are kind of zooming around, so in different directions, and at different velocities. Okay, some are going slow, some are going fast. Okay, since there's mostly empty space, they go a while before they actually collide with another one. Now when they collide with another molecule, then they bounce off in different directions with different speeds and velocities. Okay, so you can think of the simple picture of gases kind of like bumper cars. And so in bumper cars, you know, you have elastic collisions. That is to say, we don't lose energy in the collisions, we conserve energy. And so if the total energy is constant over time, the temperature is going to be constant over time. So most of the problems we're going to deal with have gas at a particular temperature. Now the most common temperature is the temperature of the room, which would be 25 degrees C, and that would be 298 Kelvin. Okay, so some of the things that we need to know about gases. First of all, that's how they behave. And this is why they expand indefinitely, because they are kind of going in a linear direction until they hit something, and then they keep going. And so they just keep banging around, and they'll eventually spread out if there's nothing to keep them from going on. So usually, of course, we prevent that from happening by containing them in a container. So we're going to call the volume of the container capital V. So V is for volume. The total energy is characterized by the temperature, which we'll call capital T. Now the important thing about the temperature, it cannot be degrees C, because degrees C has a negative part of the scale, but you can't have negative energy because energy is a square quantity. It's energy is 1/2 mv squared. Of course, mass can't be negative either, so mass is a positive number. V squared is going to be a positive number, therefore the kinetic energy is going to be a positive number. So each one of these particles has its own kinetic energy, and the temperature is the average kinetic energy of the system. Now the other thing to note about temperature is that the velocity depends on the mass. Okay, so it turns out that the very low mass molecules will have high velocities, and very heavy molecules will have low velocities. Okay, and this has an impact on the speed of sound in the material. If you ever heard somebody talk with helium, helium is very low mass material and has a very high pitched frequency because the speed of sound in helium is extremely high. On the other side, if you have extremely heavy gas like sulfur hexafluoride, that has a huge molar mass, then the speed of sound is very slow, and when somebody speaks with sulfur hexafluoride atmosphere, it's a very low pitch because the speed of sound is related to the speed of the molecules in sulfur hexafluoride. All right, so we got volume, we have temperature. The other thing that affects what is going on in a gas is that when the particles hit a wall, they bounce off the wall, and that exerts a force on the wall through Newton's law, saying, you know, for every reaction you have an opposite reaction. So if the particle comes in and then goes off with that way, well, there's also an equal force going this way on the wall, which is pressure. Now pressure is capital P. So pressure at the wall. So all of these symbols for the variables are, so this is force per unit area. Okay, so the more particles we have in here, the more collisions we have, the higher the pressure is going to be. So that's the last variable we need to indicate by a variable. So N is the number of moles. Okay? So all four of these variables are important in characterizing the gas. Okay, so one way we can increase the pressure is to increase the number of particles hitting the wall, but the other thing we can do to increase the pressure is to reduce the area. We'll make the volume smaller, or we could increase the force with which they're hitting the wall by adding more energy to the system, that is to say, to raise the temperature. So there's an equation that relates all of these variables together that we'll talk about in another video. But it turns out that the pressure in, well, there's different units, but we're usually going to use atmospheres. So the pressure at sea level of the atmosphere above us is about 1 atmosphere. Okay? And the other thing is, that is defined as being the pressure exerted by a column of mercury that is 760 millimeters high. So that's about 30 inches tall. So if you take some mercury and put it in a column 30 inches tall, the pressure at the bottom of that column is equal to the pressure of all the air several miles tall on top of you. Okay, so you need to be able to convert atmospheres to millimeters of mercury. You need to be able to convert degrees C to Kelvin. And you need to be able to convert volume in whatever units. Usually it's liters to milliliters to liters. And then, of course, moles, you should be able to convert, for example, grams to mole using the molar mass, if you need to. Now, this last conversion you usually don't wind up doing in these problems. All right, so we're just going to do a simple problem doing the conversion. So what is 475 millimeters of mercury in atmospheres? Well, there's 760 in 1 atmosphere. And so the answer is 475 divided by 760, and we get 0.625 atmospheres. Okay, so for example, you should be able to convert 25 degrees C by adding 273 and that would be 298 Kelvin. It's just a good number to know room temperature in Kelvin is 298. All right, and so gram to mole conversions we did in the previous chapter, and milliliters to liters you should be able to do as well. All right, so that's it for the intro to gases.